with functions, or not even necessarily functions, that are defined implicitly. Up till now, in this class, and in general, except for a little bit in conics back to pre-calc, you've dealt with functions and relations in general almost exclusively in explicit form. So whenever you've dealt with a function, it's been written in f of x equals equation notation, or y equals notation, and that's written explicitly. Y is explicitly defined in terms of x. Y equals some sort of x stuff. So that's an explicitly defined function. And when we take the derivative of that, it's air quotes, easy, because what's the derivative of y? Y prime. And then you only have to worry about the derivative of all the x stuff. But that's not the only way we can define functions. And there are some things that are not functions that we cannot define explicitly. So that leads us to implicitly defined functions. So if you take this same thing and we rewrite it so that y is not by itself, now it's not an explicit function. Now this is written implicitly because it's not in function notation, or it's not in y equals notation. Now, in this case, these are exactly the same thing. So this is a version of an implicitly defined function that you could rewrite in function notation if you wanted to. But there are some things that cannot be written explicitly because often they're not functions. So think of your circle equation, x squared plus y squared equals 4. That's not a function. And if you tried to rewrite it into function notation, you'd really have two equations. You'd have a plus equation for the top half of the circle and a minus equation for the bottom half of the circle. And a circle is like a simple version. So what we're going to look at in 2.5 is, what if the thing is not in function notation? What if it looks like example 0 over there, or the circle equation? Then how do we get the derivative? Because even these things have slopes at points, and so they deserve to be analyzed and picked apart and have their slopes found. Because if you were a function or a curve, wouldn't you want to have somebody come find your slope for you? No. I guess you're not very romantic. So, so in 2.5, this is going to be all about implicitly defined curves, usually not functions, and how do we differentiate them and then do all the same things that we've been doing for the last 3 weeks with explicitly defined functions. What it boils down to is all the same rules. Power rule is still a thing. Chain rule, unfortunately, is still a thing. This chain rule of this is a real delightful thing to do. Product rule is still a thing. Identifying product rule is kind of a pain. Applying product rule here is not so bad. Quotient rule is still a thing. The only main difference is now we're actually thinking about what's the derivative of y? And that's going to be dy dx. So anytime you take the derivative of a y thing, you will get a dy dx popping into your equation. So, let's do one quick example of what does this look like in practice to find the derivative of an implicitly defined curve, and then we'll come back and do the notes, and hopefully the notes will make more sense in light of the example we did. Lucas, would you please turn on the light? Thank you, sir. So we've got this equation. Probably it's not a function, so I'm going to try to avoid using the word here's a function, because usually it's not going to be. If we're defining it implicitly. So we have x to the third minus 2x to the x squared, I can read, minus 2y cubed plus 4y equals 2. And if you look at that and say, well, what if I tried to get it into function notation? Well, there's an issue with that. How many y terms do you see? 2. And one of them is y cubed and one of them is just y. So isolating the y variable would be probably impossible, or at best, just god-awful. So you're not going to do that. You're just going to take this thing and say, oh, I'm just going to differentiate this. And you're going to go term by term, and each term you're going to differentiate on its own terms. So you look at the x squared, And you say, hey, x squared, what's your derivative? 2x. All right, we're off to a good start. And then you look at the 2y cubed, and you say, hey, 2y cubed, what's your derivative? And you're going to do your power rule. So what does 2y cubed turn into? Minus 6y squared. Now, here you got to be careful, because also, what's the derivative of just y? Y prime, usually, which we'll now call dy dx. Because having both y's and y primes running around in the same equation can get confusing, because it's very easy for y prime to slowly morph into just y, as the y kind of eats the prime. So we're going to use dy dx instead of y prime, but if you like to live on the edge, you can use y prime instead. And then you say, all right, 4y, what's your derivative? 4, but also, what's the derivative of y? dy dx. So we tack a dy dx onto the 4. So anytime you take the derivative of a y term, you will do the derivative of the y term the way you normally would with x, but you also have to slap a y prime or a dy dx onto that term. Meanwhile, over here, what's the derivative of 2? 0. Common mistake is people say, oh, that's still 2. And then you have an oops following you all the way through. So just remember, if it's a constant term, it still dies and goes to 0 when you differentiate. So that's your derivative step. Everything else is algebra. Now it's a game of get dy dx by itself. Now you might look at this like, well, there's like 2 different dy dx terms. So what you do is you get all dy dx terms to one side, and then anything that does not have a dy dx gets evicted to the other side. So you look at the 2x and say, you don't have a dy dx. Get out of here. I'm like, 2x is okay. So you have minus 6y squared dy dx. He's just chilling. He's happy where he's at. Plus 4 dy dx. They've got some privacy now. They can be together, because now the 2x is over here off by himself. And the reason you do that is so that now everybody here has a dy dx. Guess what you do with that? Factor it out, because now that's your GCF. Well, I guess technically the GCF is 2 dy dx. We only care about the dy dx, so don't take out anything else except that. And you're left with negative 6y squared plus 4 behind as its own factor. And now you can isolate dy dx. Just divide the negative 6y squared plus 4 over. And you get your derivative, dy dx equals negative 2x over negative 6y squared plus 4. Oh, because we're dividing, it's going to stay the same. Like if you have negative 3x equals 9, you would divide over a negative 3. Can we reduce the fraction? Maybe. What could you divide everybody by? Okay, let's do that. So you divide everybody by 2, and you get negative x over negative 3y squared plus 2. And you could take out the negative and make it positive x over positive 3y squared minus 2, and that would also be fine. But I already wrote this, so I'm not going to change it. So that's the process of doing implicit differentiation. Ways we can make this more difficult is by throwing an x and a y together into the same term, and then you have to do product rule because you have an x times a y. Or throwing a fraction at you, and then you have to do quotient rule. Or throwing something to a power, like in parentheses, and then you have to do chain rule. And we'll look at those different situations as we go along. But this is kind of just your basic run-of-the-mill implicit differentiation problem. Yes? What would you do with this now? So that tells you the slope of this curve at any point along the curve. So if you had it now here, you have to have the whole point. You need an x and a y. I can't just give you the x anymore and say, find the y yourself. Because, yeah. So from now on, I'm going to say, here's the full point, x comma y. Use it to get the slope of the curve at that point, or use it to write the equation of the tangent line at that point. Or you could say, when is the slope going to be 0? set this equal to 0. So all the same stuff that we've done in the past, we can continue to do now once we've got the derivative. So the only new thing here is this idea of differentiating like the y stuff implicitly. Cool? Notes. Lucas, could you turn the lights back off, please? And this thing, scroll. All right, so you need to remember that y prime is really dy dx. So when you differentiate y, you get a dy dx. And in like almost sort of normal English, that represents the change in your y variable with respect to changes in x. So like as x changes, what is the resulting change in y? Is what that means. And then you've got a list of steps that you can follow as you try to do implicit differentiation. Make this bigger. You know what, given how many people are going to be out on Monday anyway, let's just change the homework that's for tonight. It's not due Monday. It's due Tuesday. I'll try to remember to like make that change in school with you. Yes, sir. So as a result of. So when we say the change in y with respect to x, x is the driving force, and as x changes, there are changes in y that result, and that's what this means. So the change in y that comes from messing with your x variable. In the next section, when we get to 2.6 and we talk about related rates, we're going to differentiate things with respect to time, even when we don't necessarily see time in the equation. So you'll have like a circle equation. Area equals pi r squared. And you're going to say, this circle is growing over a period of time. How does the area grow with respect to time? But we'll get there when we get there. We don't need, but that's kind of like the idea. So with respect to x, whatever you're respecting is the driving force. And as that changes, that forces changes in the other variable. You guys use that language in physics? Like with respect to such and such? No? Muhammad? Who's right? You do? Okay, pay attention to my brother. Maybe they did that while you were like in India. I don't know. Are you also making this? I don't know that. I've never told you. How do I ever listen to you? Oh, what's the time? Oh. So you do. Yes. Some of these curves that we look at make kind of cool graphs. So here's what this one looks like. Well, look at it. Don't judge until you've actually seen what it looks like. Okay. You're gonna look and say, "Ooh, that is cool." All right, shut up. Fine, I'm not gonna show it to you. That's not true. It's too beautiful.
The videos that would be like animations on like the TI-84 like calculator.
No, because I have a little bit more of a life than that.
No, I've never watched them.
I've never watched them. I've just seen them. Did you just say that?
No, like thumbnails.
That's about as good as I can. This is actually a little bit below. Sorry.
That's definitely why I did this. I thought it was gonna be like beautiful, yeah, like you said. Maybe like a little heart or something.
Well, there's other graphs that do that,
Yeah.
but you need to be in a totally different graphing system than what you're supposed to.
No, he's like.
So like you're all been trained in like X and Y, but what if you didn't have X and Y axis? What if you had like how much you've rotated around the origin and how far you are from the origin? So no, not Z. That's just a three-dimensional version of this. I'm talking about this is the point 1, 0. Not because you're one space away from the origin on the x-axis, but because you're one space away from the origin and you've rotated 0 radians. And then this point here is also 1, something, but now it's 1 because you're one space away from the origin. And the y-coordinate is now an angle, how much you've rotated, so that's like 1, pi over 4. So, yeah, it's cool until you have to do it, then it sucks. That's called polar coordinates. And so you can create graphs on there. There's a way to get to this in your calculator. If you go into your calculator and hit mode, this is completely off topic, so people watching this video, you can skip this part. If you go to your calculator and hit mode, you see down below radian to degree, you see func, par, pol, and sec. Go to pol for polar. Then go to y equals. And instead of y equals, now it's r equals. And if you type in something like sine of x, your calculator won't make x, it'll make theta. And if you graph that, whoops, it won't look like your normal sine graph. It'll look like, where did it go? There's nothing there. All right, never mind, don't do sine theta. I think this is going to be, I don't know what that would look like. It's been so long since I did this. I've never talked about 2 theta. Oh, that broke it. Okay, type in 2 theta or 2x and get like a spiral thing. Yeah, so that's how. So anyway, you've had enough time with the notes. We'll scroll.
It's exciting right now.
Oh, did you want to write those?
Down here?
Yeah.
Yeah.
Oh.
All right. So, you know what? You don't need to write this down. First of all, you might have an equation where the equation doesn't have any actual solution points. So that's kind of a stupid equation. Or if your equation has exactly 1 point on it. Also kind of a dumb equation. In that case, you don't have a derivative. We'll look at an example of like that probably one time exactly. If you have a section of a graph that can be represented with a function, then dy dx just represents the slope of the curve along that segment. So that's nothing particularly new, but you can take a curve and kind of chop it up into sections and say, let's only look at this particular section, and maybe that section can be represented with a function. And just a general reminder, function is not differentiable, or a curve is not differentiable if you have a vertical tangent line, because the curve goes vertical. So if you look at this base thing over here, that's like at these points where the curve is turning kind of sideways, right at that point you have a vertical tangent line. So at negative 1, 1, the derivative would be undefined. So that's what we're talking about with a vertical tangent line. Same thing here, same thing here, same thing here. So there's 4 points on this thing where the derivative would not exist. Or you can have a failed derivative when you have a sharp turn, or where you're discontinuous. So none of that is new, just kind of general reminders. You should write the thing down about the normal line. Have you talked about normal lines at all? I don't think so. Normal lines are like tangent lines, except perpendicular. So this is where we introduce the idea of a normal line. If I say, find me the equation of the normal line to the curve at this point, you do all the same things you would do to get the equation of the tangent line, except once you get your slope from the derivative, for the tangent line, you make that slope perpendicular. So it's the flipped opposite. So reciprocal, opposite, reciprocal. And we'll look at some examples of that, probably not today, but sometime next week we'll look at an example of, or two, of finding the equation of a normal line to a curve at a point. And we could have been doing that all along up till now. We just didn't because I was throwing enough other stuff at you. I didn't need to be throwing this as well at that time. So hopefully reading and hearing me talk about that was sufficient. This you should write. And when you're done these, look at example 1 over here and do A, B, and C. Or try your best with A, B, and C. And then we'll talk about D and go through that one all together in detail. Because that one's sneaky. Number D. Yes. Okay.
Oh.
It's just, hey, you differentiate this. Number A is all jumping down. So I go down. So that one is up one. Up. Does anybody need more time with the notes? Yes. So this is the derivative of stuff with respect to x. And when we take the derivative of y and we get dy dx, that's the derivative of y with respect to x. So that's why the notation is what it is. Any more time with the notes? All right. So d over dx of this stuff means the derivative of the stuff with respect to x. So that's just explaining that notation a little bit more than what I've done so far this year. Oh, bother. What is the derivative of 3x squared? 6x. And that's it. Because if you wanted to tack on like an extra thing, because we're differentiating x, that would be a dx over dx. But what's that just going to be? 1, because it's like the same thing on top and bottom, so you don't bother. So if you're differentiating x thing, I guess technically you could say dx dx, but that's just 1, so who cares? So that's just 6x. But this guy, what's the derivative of 3y squared? Yeah, so that's 6y times dy dx. Because now you're differentiating a y term with respect to x, you need a dy dx attached to that term. Lucas, could you turn the light back on, please? And go away. Now, this next one, we have separate terms because of the plus sign, so you differentiate each term on its own merits. What's the derivative of the x? 1. What's the derivative of y squared? Yeah, 2y times dy dx. And then that's it. And then this last one is similar to c, but now I've taken away the plus. So now what's going on between x and the y squared? That, wait, what? Yeah, it's multiplication, so that's going to be a product rule. So when we do our product rule, what's the derivative of the first part? 1 times the original second, y squared. Plus, what's the original first part? X times what's the derivative of the second part? 2y dy dx. Yeah, so dy dx is always multiplying the term that produced it. So then you might look at this and say this is a little awkward to look at, so maybe rewrite it so that the coefficient is in the front of that term. So it's 2xy dy dx if you want to rewrite it in a more normal looking way. And just be careful that you don't squeeze an extra plus sign in here between the x and the dy, 2y dy dx. This is derivative of the first times the original second plus original first times the derivative of the second. So if you want to label things, hey, here's the first and here's the second, that's not a bad thing. It's really easy to just read past product rule with implicit differentiation because it's so easy to just not even notice the multiplication going on between the x and the y here. So you got to really kind of slow yourself down and think, okay, what's happening? I have an x and I have a y. What's being done between them? Is there multiplication? Ah, product rule. Is there adding? Okay, proceed as normal.
So we don't have to go any further.
Correct. There wasn't like an equation. So this is just, hey, here's a term differentiated. Just practicing differentiating individual terms. Now we'll put it together and like actually get the derivative equation. Okay. Any other questions with this? All right, so now let's put it all together. That's very similar to example 0 that we started off with before we did the notes. So you guys try example 2 for yourselves right now and see how you do with it. I should, yeah. I was there last night for the, because that was my extra duty for the year to be there kind of semi-supervising stuff. She can sing. That was a very good voice. Oh, no kidding. Was anybody here in the talent show? I only caught the second half of it. You were? What were you doing? Oh, so you weren't like on stage. You don't do that. You don't get up on stage. You were in the show? I don't remember seeing you. Were you part of like the big dance team? Okay. Okay. I think the first act I saw was like 2 before Carly. So I came in like exactly halfway through. Up till then, I was busy out the doors making sure you have your ticket and ID. Cool. Please get out your ticket and ID. You don't have an ID. Well, you look like a student, so tell the people at the desk what your ID is. Oh, they don't have internet because of course we don't. Talk to one of the 17 assistant principals here. It was a fun time out there. All right, so do we have answers? Yes. What's an answer? So that's one answer. Does anybody have a different answer so that we can have an argument? Because I love arguing. That's why I had kids. No. So you have 2x plus 5 over 3y squared minus 2y? Yeah. All right. Cool. Okay. So let's go into Olivia. You have something else? Yeah. The same thing is.
Oh, it should be.
Oh, so you guys agree with each other. It's 2x minus 5. All right. So I won't put a third option. Does anybody have a third thing besides what we have so far?
When you do the derivative of y, this is the y go away because it's no longer a y. You put the dy dx with the 5, but the y is gone.
But why did it die? Because you differentiated it.
Yeah.
And what's the derivative of y? 3y dx. So let's go through it. So y cubed becomes 3y squared. Who's confused? Okay, you're in good shape. So y cubed becomes 3y squared, and you get dy dx because you did the derivative of a y thing. Then what's the derivative of y squared? And you get a dy dx because you did the derivative of a y thing. Then what's the derivative of 5y? 5. Now, do we get a dy dx? That seems to be the argument. Yes, because did we do the derivative of a y thing? Yes. So anytime you do the derivative of a y thing, out pops dy dx. So 5, y dies, you're absolutely right, but we did the derivative of a y thing, so you dy dx it. Then the derivative of x squared is 2x, and the derivative of negative 4 is 0. And it looks like nobody said, let's leave the negative 4 there, so hooray! You avoided probably the most common mistake on this sort of thing. Then add over the 2x, not the 5, and factor out dy dx on the remaining stuff. We have 3y squared minus 2y plus 5 equals 2x. Click on that. Is that Grace? Yeah. All All right, and then you divide. So there you go. And those of you that made the mistake of not having the dy dx there, it's an easily fixable mistake. No big deal. Just to see, like, what's the derivative of this thing, because this graph produces this really cool, beautiful, wonderful thing. I mean, you might call that like a vase. I don't know. What's the slope of that at 1 comma negative 3? Because we gave you that point. So, no, that would be down here, whatever that is. But I don't know what this is. But so we're at this point. You're on a slight upward trajectory at this point. So m at 1 comma negative 3 equals, what's in the numerator? 2 times 1. And in the denominator, you would have 3 times, so negative 3 squared, or let's call that 9, minus 2 times negative 3 plus 5. What's 3 times 9? Negative 2 times negative 3, plus 5 is plus 5, so that altogether makes 38, so 119. And then if we wanted to say, well, what's the equation of the tangent line to this curve at that point? You've got your point of tangency, because we gave you the whole thing, you're welcome. And you've got your slope, so you just put things together. You got y minus your y coordinate equals your slope, 1/19 times x minus the x coordinate. Ta-da! What else could we do with this? So many things. So that would be a tangent line equation at 1 comma negative 3. Or we could say, find x values where tangent line is horizontal. Because we love doing that, right? How do we find out when the tangent line is horizontal? That's when m equals 0. And so, what do we do with our m? Set it equal to dy dx. So you'd say, all right, well, dy dx is derivative, and derivative equals slope. So you set your derivative equal to 0. Now, I might look at this and say, that looks terrible. Oh, no, I did it again. But solving this isn't really that bad, because really what happens? Yeah, the denominator multiplies over here, and 0 is great. It kills everybody. And you just end up with x equals 0.
That part, you go through that one more time.
Yeah, so we want to find when the tangent line is horizontal. The slope of a horizontal line is 0. Derivatives are slopes, so we set the derivative equal to 0.
And how do you do that?
And then how do we do this?
Yeah.
We multiply both sides by the denominator. 0 times anything is 0. Over here, that cancels out and leaves you with 2x. And then you could conceivably like say, okay, let's plug 0 back into the equation and get y. Nope, never mind. We're not solving that for y. We'll just content ourselves with finding the x coordinates. You could do the same thing and find out when the tangent line is vertical. If the tangent line is vertical, what does that tell us about slope? The slope's undefined. If the slope is undefined, what part of this fraction is really 0? The bottom. Then you would take the denominator and set that equal to 0. We're not going to do that. But that would give you like the y coordinates when that happens. So we can do lots of the, like all the same stuff that we've done before, we can continue to do. We can still find points where the tangent line is horizontal, take your derivative, set it equal to 0. We can still find the equations of tangent lines. Take your derivative, plug the given point in, now you have your slope, and write your tangent line equation. We can even find out where the derivative is undefined, because that's where the tangent line is vertical. Just take the derivative of the denominator of your derivative and set that equal to 0. We'll do more of that probably Monday. One more thing, in the notes they said these weird equations where you don't have solutions or you have like a single point. So example 3a, you have x squared plus y squared equals 0. Before we try to differentiate this, Let's describe the graph of this thing. Nope. It's a circle with radius 0. So you're right, it's a circle in a certain sense, except the radius is 0. It's a point. And it's a very specific point. The origin. So this is the entire graph of that equation. Ta-da! You just graphed it. Done. Can you take the derivative at a point? Of a point? No. Because a derivative involves a slope, and a slope involves, like, 2 points. So you need to have a curve in order to get a slope. You need to have a curve, therefore, to get a derivative. If your curve is 1 point big, there's no change. And if there's no change, you don't have a derivative. So we would say here, dy dx does not exist because it's a point. Now, if we have like x squared plus y squared equals 1, now what is that shape? A circle with a radius of 1, because 1 squared is 1. So does that thing have slopes? Yeah, and then it would make sense to get derivatives. So in the notes where it said, the thing that it said, that I didn't have you write down, that's what that was about. We'll probably never look at that again. So your homework for the weekend is not due Monday, that'll be due Tuesday. So all of you taking your AP test on Monday, don't look at this homework until Monday night after you've done your AP test. And if you have an AP test on both Monday and Tuesday, or on Tuesday at all, I would recommend you just punt on this homework. Yeah, I'll be recording. Until after you're done your AP test on Monday and or Tuesday. So if on Wednesday or on Tuesday I ask you, did you do your homework, and you said AP test, I'll say, okay, cool, just show me later on in the week.